Hi, these are the solutions to quiz 27. Okay, so how much heat is released when 44.1 grams of iron 3 oxide decomposes according to this reaction here? And so heat is being released because we have an exothermic reaction. And if we have 44.1 grams of the iron 3 oxide that's decomposing, so the Q of the reaction I would take as the 44.1 grams of the Fe2O3, use the molar mass, 55.85 iron times 2 plus 16 times 3. So that's about 159.7. Oh, yeah, per mole of Fe2O3. And then here's the key. For every 2 moles of Fe2O3 that reacts, the Q reaction is minus 560.0 kJs. So when I get the answer here, 44.1 divided by 159.7 times negative 560, but divide by 2. It's this 2 here that's the most important number in the problem. Really easy to miss this. I get minus 77.3 is the Q of the reaction. So the reaction loses 77.3 kilojoules. So 77.3 kilojoules of heat's released. So the release implies the negative sign. Okay, consider which reactant is limiting versus excess. How much heat is given off or absorbed by this reaction? Okay, well, again, heat's given off because of the negative sign, and the amount of heat depends on the limiting reactant. Whichever one of these two limits the amount of reaction, limits the amount of heat change for the reaction. Okay, so we might just, we need to figure out which of these two reactants is limiting. I might say, well, how much O2 do you need to react with all of the given methanol, just from a chapter 3 perspective? So I take 15 grams of methanol. And I need to use the molar mass of methanol. So I'm dividing that by the mass of 12.01 plus 1.008 times 4 plus 16. Whatever that works out to. So it's about 32.0 grams per mole of methanol. 12 plus 16 is 28 plus 4. Yeah, so about 32 grams. And then the key here is for every 2 moles of methanol that react, how much oxygen do we need? We need 3 moles of oxygen, 1 mole of O2, 32 grams. So times 3 divided by 2 times 32 means I need 22.47, call it 22.5 grams of oxygen, and I have that much. So oxygen is the excess reactant, and then this methanol is the limiting reactant. So the limiting reactant is one that limits the amount of heat that can be given off or absorbed by the reaction, in this case given off. So what I'm going to do here is I'm going to calculate my Q reaction just like I did above by taking the 15 grams of methanol, 32.0 grams per mole of methanol. Again, the most important number here is the 2 moles of methanol from the reaction are in a ratio to the minus 1528 kJs. And remember, if you cut the coefficients in half, you cut the delta H in half, or if you double the coefficients, you double the magnitude of delta H because you're keeping this ratio intact. You got to have a ratio of kJs per mole. In this case, it's per 2 moles. So 15 divided by 32.0 times 1528 negative divided by 2. Remember, I like to keep the minus sign here and then interpret it afterwards. So I get 358 kJs negative. This is the heat given off by the reaction. So 358 kilojoules of heat is given off. Okay, so let's move on to the next question. So which of the reactions below is exothermic? Gives heat off. Liquid to solid gives heat off. And the way I know this is kind of the opposite. I know to be endothermic. If I have ice, I want to melt it. I have to give it heat. In fact, I have to warm it up for this to happen. So it has heat to absorb in order to melt. If I need to add heat to the reaction for it to take place, that means the reaction is endothermic. And so therefore the opposite reaction, liquid to solid, has to be exothermic. Liquid to gas, if I want to boil water, vaporize water, I have to supply heat in order for that reaction to take place. I don't get heat off of the reaction. If I mix two solutions together and the solution warms up, the solution's getting hotter because it obtained the heat that the reaction gave off. The reaction giving heat off is the definition of exothermic. So this reaction here would be exothermic as well. So I got A and C is exothermic. Okay, let's move on to the next question, number 4. So number 4, I have 120 grams of silver, 81.3 degrees, placed in 121 grams of water, and a coffee cup calorimeter, just an insulated coffee cup open to the atmosphere at 22.9 degrees C. The water temperature increases to 26 degrees C. We're asked to find the specific heat of silver. Okay, so here are the ideas. The Q of our silver is the negative the Q of the water. So silver is losing heat as the water is gaining the heat it gives off. And so we have the MCS delta T for silver equal to negative MCS delta T for water. And I have pretty much the information to calculate both sides of this equation here. Like I can plug in, I have 120 grams of silver times whatever its CS is, that's going to be our unknown. And the delta T of silver ends up at the same temperature the water ends up at. So the final temperature of silver and water are both 26 degrees. So 26.0 minus 81.3 means silver temperature dropped by 55.3 degrees C. And the mass of water here, 121 grams of water. So I got to keep my minus sign here because the relationship between one of them obtaining the heat, the other one's losing. 4.184. Specific heat of water. The delta T of water is 26 minus 22.9, so that is 3.1 degrees C. And so we're just going to solve for CS here. So I'll do 121 negative times 4.184 times 3.1 divide by 120 times negative 55.3. So my CS comes out to be equal to 0.237 joules per gram degree C. Next page, a 4-gram sample of methyl hydrazine completely combusted in a bomb calorimeter with the total heat capacity, including the water surrounding the calorimeter, of 7.79 kilojoules per Kelvin. Calorimeter was initially at 25 degrees C. Prior to combustion, increases all the way up to 39.50. What is the heat release per mole of the compound? Okay, so the idea here, heat change of the reaction, is the negative heat change of the surroundings. In this case, the surroundings is the entire calorimeter, including the water that surround the bomb cell. Calorimeter is described as an object as the heat capacity times a delta T. Notice there's no unit of mass here, just heat per Kelvin, so just heat capacity times delta T. So the heat change of the reaction, not of this full reaction, but the reaction actually occurring inside the calorimeter, the reaction just the 4-gram sample. So the reaction in the calorimeter, its Q reaction is negative heat capacity of the calorimeter times the delta T of the calorimeter. Delta T is final minus the initial temperature, so that's 14.500 degrees C. That cancels. If you don't believe me, then I don't know what to say. But convert both to Kelvin, then take the difference and see it's 14.50 Kelvin. But hopefully we're all on the same page on that part of the problem. Negative 7.794 times 14.5. So the Q reaction, but the reaction inside the calorimeter, negative 113.01 kJs. Now, that might be a choice. Surprised it's not a choice. It doesn't look like it's actually a choice. But sometimes you might see a number like this that looks like the choice. But the key is, this is the heat that's released per 4 grams of the compound. If we want the heat per mole of the compound, we just got to go grams to moles. Let's see. We weren't given the molar mass inside the problem of the compound, so we just got to look at the formula here. So we have, we're going to divide the negative 113 by 4 and then multiply it by the mass of 12.01 for 1 carbon. I see 2 nitrogens, so 14.01 times 2, and then plus 1, 2, 3, plus 6. I got 6 hydrogens. 6 times 1.008. That gives me negative 1301. So whatever this molar mass is here, number of grams per mole of the methyl hydrazine, that gives me minus 1301 kJs per mole. Or call it 13.02 with rounding. So the answer to the question would be C. Now if we ask, what's the delta H of the reaction? What's the delta H of this balanced reaction? That's another question we can ask, is what's the enthalpy change for the balanced reaction? Well, we just got to take the 1302 kJs times 2 moles. So the delta H of this reaction, as it's balanced here, would be the 1302 times 2. So it's 2604. Now remember, negative, almost all of these choices are negative. I guess 3 of the 5 choices are negative, but negative because it's exothermic. Exothermic because it's making the water temperature go up. Okay, let's look at next question. Consider the below combustion reaction of methanol in the presence of oxygen. So we have 2-methanol plus 3O2, go to the products, delta H is shown. How much methanol must be combusted in order for the increase of temperature of 25.5 kilograms of water? Okay, so we're trying to raise the temperature of water using the heat given off by this reaction. So we want to raise 25.5 kilograms of water from 25 to 95 degrees C. Specific heat of water is given here. So the heat that water has to absorb in order to undergo this change here would be the MCS delta T for water. So 25,500 kilograms, or 25,500 grams of water times 4.184 times 95 minus 75, that's 70 grams, and then divide by 1,000 joules per kilojoule, gives 74.68 kilojoules. That's how much heat has to be absorbed by water in order for it to increase its temperature by 70 degrees. Now, if the heat's coming from this reaction taking place, so heat's being given off by the exothermic reaction, we want to know how much methanol is needed in terms of number of grams. What I would do is I would take the plus 74.68 kilojoules that I need to have water absorb, and I'm getting 1528 kilojoules for every 2 moles of methanol that react, and 1 mole of methanol has a molar mass of 32.04 grams. So I go 7468 times 2, divide by 1528 kilojoules being given off, times 32.04 to go per gram. It gives me 313 grams. So 313 grams of methanol. If it were to combust, let's actually do this problem again. Let's do a double check here. So I take 313 grams of methanol, convert it to moles, so I divide by 32.04. That gives me about 9.77 moles of methanol. Now for every 2 moles of methanol that combust, I get 1528 kilojoules of heat. That corresponds to 7464. So with rounding, that's giving me the 7468-ish kilojoules I need to heat water up. So 313 grams of methanol. So consider this reaction here of OH plus Cl2 goes to HOCl plus Cl. Calculate the delta H for this reaction here. We want to find the delta H for this reaction here using these reactions down below. Okay, and so this just becomes kind of like a word problem, or a puzzle maybe is a better thing than a word problem, of just how do I need to manipulate the reactions to add up to our desired reaction. Now my trick, if you will, is trying to spot something like Cl2 is only in one reaction. You know, like I'm just like inspecting these reactions and just looking for Cl2. And I see Cl2 is only in this reaction here. And it's on the right side, it's on the reactant side of the reaction, and there's the proper number. So I don't need to change the first reaction at all. So this reaction here is just being used as is. Second reaction, or just another substance like OH here, is only in the second reaction. So I'm just like looking for all 3 reactions. Is OH in the reaction anywhere? If it's in 2 of the reactions, I'm going to skip and look for a different substance. But OH is only in the second reaction, but it's on the product side. So I need to flip the reaction. Then I also need to cut the coefficients in half. So I need to flip the sign of delta H to flip the reaction. And I need to cut the coefficients by half, so I cut the delta H magnitude by half. And then the final reaction, I have the HOCl2, or excuse me, the HOCl, but I just have 2 of them. So I need to cut the coefficients of this reaction by half. And then, but the product's on the right side of the reaction. It's on the correct side of the reaction. So if I flip the second reaction and I have OH going to a half H2O2, that's what I accomplished by cutting the coefficients in half. The delta H of that reaction would be minus 134 by 2, so minus 67.0 kJs. And in the second reaction, once I cut the coefficients in half, get 1 here, half here, so the half H2O2 cancels. The chlorine atom cancels, but one of them, so one of the chlorine atoms cancel, and I'm left with just one. I add up Cl2 plus the OH radical goes to the products of Cl plus HOCl. And the only thing I need to do is take 209 negative divide by 2, so minus 104.5 is the delta H for our manipulated reaction for the third reaction. So I'm doing 242 for the first reaction as is, plus negative 67.0, plus negative 104.5. I get 70.5 positive. So it's just kind of a puzzle, just trying to see how you need to manipulate the reaction so you can see how you need to manipulate the delta H's. Whether or not you actually physically rewrite the reactions and show them adding up and balancing out kind of depends on the complexity of the problem. If you understand, when we're cutting the reaction like coefficients in half. Like, you can probably piece it together without rewriting the reactions. But if you want to be careful, just physically rewrite the reactions, or maybe somewhere below, physically add up the reactions and make sure they give you the desired reaction. Last question, we have a coffee cup calorimeter problem here. So coffee cup calorimeter contains 125 grams of water at this temperature. 10.5 grams of ammonium nitrate's added at the same temperature. And the solution drops. Solution temperature drops to 18.30 degrees C. What is the enthalpy of solution of ammonium nitrate in kJs per mole? Assume the enthalpy of the solution is that of water. Okay, so here's how I might approach this problem here. Q reaction, always the opposite of its surroundings. Here the reaction surroundings is the solution it's taking place in. Now my Q reaction is the negative of the solution. The solution is described by an MCS delta T. So Q the solution, MCS delta T, so I keep my minus sign for the minus Q solution. And these are all for the solution. So that helps me know that the mass I use is the mass of the solution. So mass of the solution, 10.5 plus 125 is 135.5 grams times the CS. We're told it's 4.184 joules per gram degree C, and then times the delta T. Temperature is dropping. So I'm pretty sure I have an endothermic reaction due to the temperature dropping, because heat's being absorbed, leading to the solution temperature to drop. Negative 5.9 degrees C. Just make sure to take your final temperature minus Ti. So minus 5.9 degrees C. So the Q reaction is minus 135.5 times 4.184 times negative 5.9. And then I'll even convert over to kilojoules, so I'll divide by 1,000 joules per kilojoule. Leads Q reaction to be positive 3.34 kJs. Now the key is that this is the reaction actually occurring in the calorimeter. So it's the reaction of the 10.5 grams. What I want to divide by in every case is whatever the limiting reactant is. What limits the heat of the reaction is the reaction itself. So the only reactant here is the 10.5 grams of ammonium nitrate. And we can also pick up, we want to divide by the mass of just the ammonium nitrate as opposed to the mass of the water or the mass of the two added together. It's because we want the heat change in kJs per mole of ammonium nitrate. So to get to per mole ammonium nitrate, I need to start with the mass of the sample that actually was inside the calorimeter. Now we're given the molar mass. Make sure, some problems give you the molar mass, so you don't have to spend time calculating it. 80.04 grams per mole of ammonium nitrate. So we do 3.34 divided by 10.5 times 80.04 gives me plus 25.5. Okay, so you just want to go from the heat change for the reaction in the calorimeter and then work that out in terms of kJs per mole. Okay, that's all for this activity. Thanks for the attention.